Hey guys, this is Jay. Welcome back to a new video. Today we'll cover a few topics. MO theory on conjugated dienes, preparation of dienes, kinetic product, thermodynamic product, and Diels-Alder reaction. So here are two important key phrases, Homo and Lumo. Homo is highest occupied molecular orbital, and Lumo is slowest unoccupied molecular orbital. If we were to draw the Homo and Lumo of a conjugated diene, we first count the number of carbons. Then we draw out these molecular orbitals and fill them with pi electrons accordingly, with the bottom level having the lowest energy. Thus, it should be the one with zero node. A node is when p orbitals aren't overlapping, like here, and that increases energy. From bottom to top, add the number of nodes by 1 for each successive energy level. Select the two levels in the middle. The top one would be Lumo, and the bottom one would be Homo. Another way to reinforce this idea is that pi electrons only fill all the way up to Homo, hence the term highest occupied molecular orbital. Preparation of dienes. So it can be formed by using E2 reaction twice. Just note that the base we use will influence where the alkene will go. Hofmann product used less substituted alkene and is favored with bulky base, such as DBU. And Zaitsev product used a more substituted alkene and is generally favored. Here we use NaOH. So kinetic and thermodynamic product. The kinetic product has a more stable intermediate or lower activation energy and is favored at lower temperature, while the thermodynamic product has a more stable or lower energy product and is favored at a higher temperature. One of the examples we went over in class is hydrohalogenation of a conjugated diene. So recall hydrohalogenation of alkene used a hydrogen and halogen addition, with the halogen adding onto the more substituted carbon and the hydrogen adding onto the less substituted carbon. It forms the carbocation intermediate after the pi bond grabs the hydrogen. Then the halogen will come and attack the carbocation. So here, the top product is kinetic because it has a more favorable intermediate, secondary carbocation versus primary carbocation at the bottom. The bottom product is thermodynamic because it has a more favorable product, tri-substituted alkene versus monosubstituted alkene at the top. Another example we went over is halogenation of conjugated diene. So recall halogenation of alkene with U and anti-addition of halogen on each of the carbons participating in the alkene. It first forms an intermediate, then the chlorine or the halogen will normally attack this carbon and the halogen gets kicked off. So here, the top product is kinetic because it's easier for the second halogen to attack at a carbon that is closer, proximity effect, which allows it to have a lower activation energy. The bottom product is thermodynamic because it's more favorable, di-substituted alkene versus monosubstituted alkene at the top. All right, so Diels-Alder reaction. This is one of my favorite reactions. So a diene and a dienophile would react to form a ring. The products are favored at lower temperature, and the reactants are favored at higher temperature. The reason is as follows. So the equation delta G equals delta H minus temperature times delta S. And if delta G is negative, then the reaction is favored. Delta H, or change of enthalpy, is negative for this reaction. Delta S, or change of entropy, is also negative because a ring is being formed, so less degree of chaos. So at higher temperature, the delta G is more positive, so the reactant would be favored. And at a lower temperature, delta G would be more negative, so the product would be favored. So now let's get into the two components of this reaction, diene and dienophile. The dienophile is usually electron deficient, and it can have EWG or electron withdrawing groups such as nitro and carbonyl along it. It has alkene or alkyne for some kind of pi bond. If the dienophile has cis substituents on alkene, then those substituents will show as syn on the product. If the dienophile has trans substituents on alkene, then those substituents will show as anti on the product. The dienes is usually electron rich, but note that only S cis is reactive. The S means sigma, so S trans would be two double bonds adjoined by a sigma bond, but the double bonds are pointing in different directions, and S cis would be if they're pointing the same direction. Though some S trans can convert into S cis because sigma bond is capable of rotating, there are some S trans that can't do so. So these sigma bonds can't rotate because they're in a ring, which would give us lock S trans, which is not reactive. And here we have lock S cis. The sigma bond cannot rotate because it is in a ring. So we get lock S cis, which is quite reactive. So thank you guys for watching and see you guys next time.